Hello to those watching this in the future online. It's semester 2, 2024, and this is the revision seminar for data analytics. I've already done the spiel about how it's going to work, and now I have to choose something to talk about. All right, well, I got an email last week. That's someone going to all the effort of sending me a request early. I think I should talk about that one first. And it was about probability, and in particular, conditional versus marginal probabilities. Is that a terminology that's in this course? Good. I'm glad. I'm reading the email from the right course. The 2023 semester 1 seminar started with a discussion of probability and about what union and intersection are like in that context, and conditional probability in that context. But I didn't talk about conditional and marginal distributions. And so I thought I'd start there. So just the short version of this of probability is that all probabilities are a comparison between what you're thinking of and everything that could be. And I've been very careful to say what you're thinking of, because sometimes everything that could be. The reason I've said what you're thinking of, sometimes probabilities are what's the probability of this future event happening compared to all the things that could happen in the future. And sometimes probabilities are what's the probability of this event that's already happened compared to all the things that could have happened. So sometimes it's about the future and sometimes it's about the present. But it's the same idea. You compare to what could be, and that is what a probability is. And so therefore, the only way to know a probability is to know all the things that could be. And it's a very important thing to hold on to when you do probability. It's like, okay, so ask me the probability of an event. I need to know what all the other events could have been, so that I can compare what I've got to those. And most probabilities belong to some sort of object or some sort of moment in time. And so sometimes probabilities belong to like a day or a minute, and sometimes they belong to an event, an object like a pair of dice or a person. And it's useful to know what thing the statements you're making are about. So you need to know what objects you're thinking of. And I know that's vague, but it's really important. So if people talking about probability and they say, the probability of this thing happening is whatever it is, like a third, you go, okay, are you talking about both dice at once or just one of them? Or are you talking about the group of 10 people or just one of those 10 people? And it's really important to keep that in mind about exactly what thing the probability is about. And in a conditional sort of marginal distribution situation, your object has at least two ways to measure it. So you may have, give me a second. They're coming up with examples off the top of my head. You can see why they write exams like months in advance and get people to check them, right? Because it's really hard to come up with the problems so that they work. I'm going to make an example. That's definitely what I'm going to do. And then okay, here's my scenario. It's do I like it? Okay. I'm going to roll 2 ordinary dice. So someone says roll 2 dice and they don't say that they're 6-sided dice. They always mean it's 6-sided dice. Roll 2 dice and write down the total. And the difference. The difference meaning how far apart they are. So if you wrote a 4 and a 6, you'd write down a 2, because that's how far apart they are. But if you roll 2 6s, you'd write down a 0. Okay. And so the thing that we're imagining is the 2 dice being rolled, and we've written down 2 pieces of information, the total and the difference. So in conditional and marginal distribution situations, there are at least 2 things that you've written down about each thing. And in my story today, the thing is the pair of dice together. Because the difference doesn't belong to one of the dice, it belongs to both of them. And the total doesn't belong to one of the dice, it belongs to both of them. So the total has all these numbers it could be. It could be 2, 3, 4, all the way up to 12. That's what the total could possibly be. And the difference could be, I guess, anything from 0 to 5. They can't be 6 apart because they're only numbers from 1 to 6, right? Yeah, 5. Okay. So they're the options. And some differences can only go with some totals. Like you can only get a total of 12 if you roll 2 6s, and that would go with a difference of 0. Whereas a total of 11 has 2 ways to do it, and each of them would go with a different difference. And so it's not like, yeah, so that sort of situation is a very marginal and conditional probability situation, where the different options in one way of measuring a thing go with some of these go with different amounts of these. That's sort of how those ideas work. So this may not be a good example, but I'm just saying that these 2 pieces of information aren't independent of each other, because when you know what the difference is, then there's only so many totals that go with that. And vice versa, if you know what the total is, there's only so many differences that go with that. And it's not always the same ones. And so knowing about one of these numbers changes what you know about the other one. And that's called being not independent. But if they're independent, then no matter which total you got, you'd be able to get that total with any of the differences. Okay, how do you feel about that? Okay, so a joint distribution is a distribution that just like, so these pair of dice and these numbers, each combination of difference and total has its own probability to go with it. And that's a joint distribution. So if you know what the difference and the total is together, you should be able to figure out the probability of getting a total of 4 and a difference of 1 at the same time. That should be a thing that you can do. And that's called a joint distribution. It describes the probability of combinations of things. So in this story, I really shouldn't have done 2 6-sided dice. There's way too many options. That was a bad idea. But you could, for example, you could write down the probability of getting the total equals 2 and the difference equals 0. That would only happen if the dice were 1 and 1, right? Yeah, so for the total to be 2, you can only roll that with 1 and 1. And then the difference is 0, so that's good. And so that probability is probability of both dice 1. And that happens, well, there's a sixth of the time for the first dice being 1 and a sixth of the time for the second dice being 1. So that's 1 in 36. But this is not a very good example. I'll give you a better one in a second. If I had the total being 2 and the difference being 1, well, that's impossible. For the total to be 2, the only way to do that is for the both dice to be 1 and then the difference is 0. So this is impossible because it doesn't ever happen. And if I had the probability that the total equals 3 and the difference equals 0, well, that's impossible because if the difference is 0, the two dice are the same. And when you added them together, you would get an even number and you couldn't get 3. So that's impossible. And the probability that the total equals 3 and the difference equals 1, that's okay. You could get dice show 1 and 2. That's how to get a 3. And I think that happens in 2 ways out of the 36 if I look at the big table. So my way of solving this problem would actually be to draw a great big table of all the ones and so the first die and the second die. And they have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, like that. And these are all of the ways that the 2 dice could come up. And every one of those happens the same number of times. And so I'm looking for a 1 and a 2 and a 1 and a 2, and that happens 2 out of the 36 times. Yeah, and so this is a complicated example. The same as 1 in 18. This is a complicated example, and I made it that way deliberately because when I'm looking at this, these are all the different ways that you could get all these different answers. And you could make a big table of the total, which comes as 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the difference every one of these would have a probability to go with it, but they're not all the same probability. So we already figured out that to get a total of 2 and a difference of 0, that's 1 in 36, that probability. And a total of 2 and a difference of anything else, they're all 0. And a total of 3 and a difference of 0 is none. And there's 118 there. And I reckon all the other ones are 0. And a total of 4 and a difference of 0, that would need a double 2, so that'd be 1 in 36. And a total of 4 and a difference of 1, well, that's impossible because you'd get an odd number if they had a difference of 1. And a total of 4 and a difference of 2. Oh, damn it, I haven't got any more that have got any other numbers in them. Okay, wow, that's not, I'm very surprised as to what's happening here. And then a total of 5 could be a 2 and a 3. That'll be here. And eventually we'll start to get ones that have more than one way of doing it. So I'd never thought of this problem before, so I'm very surprised as what's happening here. It is not common to have mostly zeros in a table like this, but there you go. It's one of those things. And every one of these can have a probability figured out. And the idea is that this big grid covers all of the possible ways that my 2 dice can roll. And so the entire total of all the probabilities must be 1, because these are all the different ways that you can get a total and a difference on a die, on 2 dice. Right. Anyway, different story. It's much more common for people in a course like this to just give you a random table of some random numbers. where you go X and Y are random variables with joint distribution as shown in the table. And you have like, these are the X's. So this one's going to come in flavors of 1, 2, 3, and 4, and this one will be 1 and 2, something like that. Much more common to get something smaller, and they'll just randomly fill in some probabilities for you. And so what I'm going to do is I'm going to make the big numbers more likely when I have a 1, because I'm just making up my problem today. Oh, I do not want that to be quite so big. What are we up to so far? 0.5. Cool. So that was 0.5. And this is 0.2. And then that's another 0.2. And that's a 0.1. So that's 0.5 as well. So the total of the whole thing is 1. So this is a valid joint distribution because all of the probabilities add up to 1. And so what this is telling us is there is some object, maybe it's a person, maybe it's a die, some dice, or a coin, or who knows what, some object, I'm going to say they're people, where I can measure what X is and measure what Y is for each person. That's what I'm imagining in my head. They're always people if I don't know what they are. So maybe this is the number of Nanny McPhee films someone has seen, and this is the number of, what are there 4 of? Thor films somebody has seen. There you go. So they're more likely to have seen less Thor films if they've seen more Nanny McPhee films. I'm making up crap. Sorry, I'm just thinking about that. But these are 2 pieces of information about the same person. And so then I can ask myself, are these 2 variables independent? And I can see already they're not, because when X is 1, it's more likely for Y to be 4, but when X is 2, it's most likely for Y to be 1. So they're not independent because knowing about one of the numbers changes how likely the other numbers are. Yeah. And I can also know in lots of other ways. So a marginal distribution is if you just got a whole lot of people and you only wrote down what X was and you didn't write down what Y was, then how likely would the different options for X be? That's the question that we're asking ourselves when we do a marginal distribution. And same for Y, we could just have a whole lot of people and only write down what Y is, even though we know they have an X. I'm only going to write down what Y is. How likely would their options for Y be? And that means you have to combine everybody who's in the 1s and the 2s for X's because we don't know which one they've got. We have to join them together into one big group. So we can actually have a total when you combine the options for X, and my totals are 0.2 here and 0.25 here and 0.2 here and 0.35 here. That there is the marginal distribution for X. No, for Y, sorry. Because what it's saying is that no matter what X is, among all the different options for X, this is how likely it is to be 1 for Y. So the marginal distribution for Y is one, two, three, 4. They're the options for what Y could be. And when I combine all the X's together, this is what I get. And I can check if I've done my maths right, because the total should be 1 still. 0.25 and 0.35 is 0.6. And then there's another 0.2, which is 0.8, another 0.2, which is 1. Okay, so they still add up to 1. How are we feeling? Okay. And the marginal distribution for y is completely ignoring what y is, for x, sorry, is completely ignoring what x is. Marginal distribution for x is completely ignoring what y is doing and just saying, well, how often do we get 1 and how often do we get 2? Which means we have to combine all the y's together. And so we've got 0.5, because I set it up that way originally, so that's fine. So the marginal distribution for x, these are the options for what x is, and the probability that x comes out to that answer is 0.5 and 0.5. So that's how you do a marginal distribution. And they're called marginal distributions because they are written in the margins of the original table. It's not a very creative name, but and weirdly, it doesn't, if you didn't know that you were drawing it in a table, the name wouldn't make any sense. So you can think of it, if you like, as the ignore the other distribution. You're ignoring what the other variable is doing and trying to combine it together. Yeah. Okay. That is marginal distributions. A conditional distribution happens when you're doing a similar thing, but you're specifically not ignoring what x is doing. You're saying, well, just a second, I only want to look at the ones that have a specific value of x. So if you have a conditional distribution, conditional, of y given that x is equal to 1, so that's how I would write it, then that's saying that only out of the ones where x is equal to 1, how likely is it to get the various options for y? So I could look at this and I go, oh yeah, there's a 10% probability of getting a 2 for y, and I'm ignoring all the ones where x is equal to 2 because I'm only interested in this one. But the thing is, these probabilities don't add up to 100%. So what I'm saying is that my new 100% is only the ones that have x equals 1. So I'm going to have to say, oh crap, this isn't 0.1, it's 0.1 out of 0.5. I have to readjust and divide everything by this total to make it into so that it adds up to 1. That's what you have to do. Conditional distribution y given x equals 1. I'm going to have to do, this is y. This is probably that at y equals y given that x is 1. And I have to do 0. Well, that's always going to be 0. I have to do 0 divided by 0.5, 0.1 divided by 0.5, which is 0.2, and 0.1 divided by 0.5, which is 0.2, and 0.3 divided by 0.5, which is 0.6. And so my actual probabilities are 0, 0.2, 0.2, and 0.6. And now they really do add up to 1, because that plus that plus that is in fact 100%. And that's a conditional distribution. And if I did the one for x equals 2, then it would have its own distribution, and they're not the same as each other, so you know they're not, just a second, you know they are not independent. And if I did the conditional distribution for x given that y is equal to 2, then I would get x, the probability that x is equal to x given that y is 2. So x can only be 1 or 2. That's these options. And the probability would have been, when y is 2, the probability would have been 0.1, but I have to divide by the total. And the probability would have been 0.15, but I have to divide by the total. And so I get, no, I don't know, 0.4 and 0.6. See, I didn't choose this one because I couldn't do that one in my head. But if I had to do that one, I would have to use a calculator and divide by 0.35, and I'll get a terrible decimal that I'll have to round off. Yeah. Okay. I mean, the point of this is saying that, look, if y is equal to 2, it's more likely to be for x to be 2 than it is to be 1, according to this calculation here, which still works here. Like, it's more likely to be 2 than 1. But it's exactly how these are compared to each other. And then there's one final thing I need to say, is that often you're not told these probabilities to begin with, and you're just told raw numbers. You're just saying, we've had 500 people, and we counted how many of them had y is 2 and x equals 1, and this is how many people were in that spot. Well, it's the same deal. You just have to turn everything into probabilities by dividing by the totals. So just as an example, if it was this same story, and instead of probability, this is the number of people, it's not going to be the same numbers. Sorry. And if you had number of people that were in each spot, if you wanted probabilities, you'd have to be dividing by totals. And so I could do the totals. 21, that would be 28, this would be 20, and this is 37. And the total of all of those is 69 plus 37, which would be 70 plus 36, which is 106. And then we could do the totals this way as well. 35 and 11 is 46, 58. And let's see, we have 30, 46, 40. And yes, that works. Yes. Okay, cool. The total this way should be 106 as well. So that checks if I've done my maths right. I mean, this is what calculators are for. But I like to practice my mental arithmetic when it's not important, so that I'm better at it when it is important. Okay, so this at the moment is not probabilities. These are just raw numbers of people. And if I wanted them to be probabilities, then I would have to divide by the appropriate total. If I wanted the joint probability table, then that is all of these options compared to the grand total. So to get joint probabilities, I divide by the grand total of 106. To get the marginal probability of x, so if I've got the marginal probabilities for x, I'm ignoring everything that y is doing, and I'm just looking at this 1 and 2. And so I would divide that thing still by the grand total, but I'm dividing the margin by the grand total. So I'm dividing the inside by the 106, and this is the margin by 106. But if I want the conditional probs for x, given that y is, no, I'll do y. For y, given that x is, say, 2, now I'm looking at just this story here, and so I'd be dividing by the 48, because that's what the total is of just those ones I'm looking at. Yeah. So I guess figure out what part of the table you're looking at. When you're looking for the joint probability, you're looking at all of this and just that grand total. When you're looking for marginal probabilities, you're only looking at this and you've got a total. When you're looking for a conditional probability, you're only looking at one row and it's got a total of its own. So you have to divide by the total that belongs to that row or that column. How are we feeling? I'm going to say, if you don't feel brave to talk about it here, Maths Learning Centre is open all week. And in particular, I'll be there in the afternoons after the revision seminars finish, about 2 o'clock every day. And from Thursday and Friday, I'll be there all day. So, no. Generally there in the afternoons this week, because I have other people that I have to look after in the mornings. But all the tutors can help with things, especially if you help them, show them the bit of the MyUni that you're looking at. They're really good at interpreting what's in MyUni. So, okay, all right, that'll do with that. And the question I didn't answer is, why do we care? Well, every time, I don't know. Yeah. Sometimes statisticians, economists, and mathematicians just get interested in stuff. And I would bet you that at any time you said that people could have 2 features, you would wonder whether it was more likely for one thing to happen than another. You probably wouldn't want to do the actual calculations, but you'd wonder. And so it's natural to wonder about some of these things, about how likely something is if you're only in a certain situation. It's much less natural to actually do all the calculations, but it's a stats course. That's just the way it is. So, yeah. I'm going to number these pages now before I forget, or I'll be in grand strife when I try to scan them later. And so the notes will be on the Maths Learning Center website. Yeah. Okay. Looks like we've got some things with some Z tables and T tables and stuff. Maybe we'll have a look at that. I'm at a slight disadvantage here because I can't see inside your MyUni. But if I just Google a table, it should be roughly the right one. We can find the one that matches your story. So using... The interesting thing about using tables is that it's not, as the question is said here, there are lots of different situations when a table turns up. So let's see if we can think of them. So I have some situations where a table turns up. There are times when you've been given a straight up probability problem about a normal distribution, something like that. That's one of the times that the probability tables tend to turn up. And then there are times when you are calculating a confidence interval. That's another time when a table turns up as well. And the other time that a table turns up is when you're doing a hypothesis test. They call it hypothesis test or significance test in this course. Hypothesis, okay. One of those terminology differences. And I just want to check something. Do you calculate p-values in this course? Do you also do rejection regions? Of course, that. Yeah. Okay, so I think this is pretty much all the time when you do them. And there are different flavors of hypothesis tests that will require different tables. Okay, cool. I'm just going to put them together again and say the Z or T test, maybe. Okay, just making sure. I think that's pretty much it. Confidence intervals come in Z or T as well, don't they? Cool, just making sure. So I'm almost certain that there are two tables, I think, in this course. There's a big Z table and there's a T table. I think that's all of them, yeah? Good. Some courses have a few other ones as well. But actually, most courses don't use tables. They get the computer to calculate it for them. So, yes. With the invention of Excel or any other computer program, we probably don't need the tables anymore, but that's okay. Some people think that it is an important rite of passage to have to use the tables, mainly because they had to use them when they learned it. And the antelope eat the grass, and we're all connected in the great circle of life. That is how many lecturers think. They learned it with tables, and they believe that the learning of it with tables made them understand it better. And here we are. So we have to learn it regardless of whether we agree with it or not. So I want to say that the tables are both trying to describe the relationship between the value of T or Z and the probability that goes with it. And depending on what your tables look like, is how they are arranged that way. And I'm almost certain that the Z table is in the reverse direction to the T table. This will make more sense when I find one. So, does anyone happen to have one handy, or do we know where to find it in my uni? Because I know that that's like 10,000 clicks to actually find the page you want. But if not, I can just Google them. I got one. I'll come have a look, and then I'll speak back and see if I can find. Actually, you can put it down on the email. Nothing back to the email that you can have work. Okay, have some thinking music and, go to the toilet, have a break, and we'll sort it out. But while we're looking that up, I'm just going to give the vibe. So the idea is that big idea is that there are distributions, and a distribution describes all the probabilities, like how likely all of the options that could be are compared to each other. And our Z distribution, which is the standard normal distribution, sometimes known as N01, where 0 is the mean and 1 is the standard deviation. Looks like this. And what that height there means is that the higher the height of that graph is, the more likely it is to be nearby to that point. Thank you. Looks like it's come. The more likely it is to be nearby to that spot. And so it's much more likely to be nearer to 0 than it is to be nearer to anything else. And the further out you go, the less likely it is to be near that spot. But the height isn't the probability, it's the areas that are the probability. So the only way to talk about normal distributions is to talk about the probability of being in a certain zone on the axis. The other thing to know is that this point where it stops coming down and stops going down like that and starts going out like that, that's the one, but it doesn't really matter. And 2/3 of the areas in this spot here, basically, that's how a normal distribution works. I don't know, I discovered it like, 120 years ago. And it does a pretty good job of describing how far things are from their mean for most measurements that you take on humans, or on fruit or grain or bugs or whatever. It's like, things, living things generally, and actually quite a few non-living things. If you measure them then and draw a nice graph of how likely everything is, it tends to look like this. And importantly, for both for economics and for psychology, if you add together a large number of scores that are out of the same total, then you tend to make something like this as well. And so when psychologists give you this long survey and you get all these things out of 5, if you add them all together, it'll tend to be this sort of thing. And when you roll like 7 dice and add them up, adding up a whole lot of things that are out of the same total, it tends to make this sort of shape too. So that's why it's called the normal distribution, because it's ordinary, it happens all the time. Anyway, that was not really relevant. The standard normal distribution has 0 in the middle and 1 there and -1 there. And you've almost got all the probability once you get out to 3 and -3. It's almost all there. It's technically possible to get numbers that are further out, but it's really unlikely. And when they make the table, and when Excel makes its calculations, they don't tell you, the table doesn't tell you the height of this graph. What it tells you is the area so far coming in from the left. So when you draw a table, table tells you, if you're at a particular spot, what the area coming in from the left is so far. And the further you move the Z, then the bigger that area is going to get. That's the idea. So table gives you area coming in from the left. Now I'm actually going to show you the table. Once it opens. No, well, I've lost my window. There it is. So this is the standard table that is provided in your MyUni. And you'll see the note at the top in the title says, table values represent area to the left of the Z-score. So as you come in from the left and you're at -3.9 so far, at this spot just here, the area so far from the left, once you come in all the way from the very far left and arrive at -3.9, so far there's 0.00005 out of 1, that area has been covered so far. And as you move through the 3s, that probability doesn't go up very fast. Like these all say 0.004, and presumably in like the 7th decimal place, the numbers are getting higher and higher. So it's probably 0.00401 and 0.00403 and whatever. And they're getting higher and higher until eventually this is 0.00044 maybe, and then it rounds off to 0.003. And again, it goes up very, very slowly, but the closer to 0 that you get, the faster those values are going up. So here at -2, where these probabilities are getting higher quicker. And if I'm going to talk about how to read this table, when I have like -3.3 here, this is the probability that goes with -3.30. This is the probability that goes with -3.31. This is the probability that goes with -3.32. And you get your whole number part in your first decimal place here. And then this one goes with each new decimal place as you go. So as you go along this way, you are moving from left to the right on that diagram that I drew earlier, moving from left to right. And then you go down to the next table to keep going from left to right. And then you go down to the next one to keep going from left to right. Yeah, but when you're here at 0, when you're close to 0 here, the probability is actually going up quite fast at that point, because the height is the highest there. So as you move along, you get more area added as you go. Oh, fuck, I was wrong. Damn it. It's this one that moves to the left. Sorry, because that's 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, and 0 0.1. This one moves the other way because negative numbers, when you make the decimal part smaller, they actually are technically moving to the right. Oh, no. So I now know that if I made one of these tables myself, I would have put the 9s on the left for the negative ones, and I would have put the 9 on the right. Ugh. As you can see, even someone who learned to read this table can still describe it wrong. So pay attention. Ultimately, if you're just reading it, you don't have to actually know which direction it's going. You can just find the one you want. So if I wanted, for example, to know the probability that Z was less than 2.74, then I would go to 2.74, and the probability of Z being less than 2.74 is 0.00307, which is very small. Yeah. But it only tells you probabilities of being less than. Sorry, minus 2.74. Whereas if I wanted less than 1.83, then I would go to 1.83, which is here, and it's 0.96562, like almost at 100% when we're all the way over at 1.832. That's 1.82. That's 1.83. There. Okay, so that's how to read the table. And it's important to note that what this table tells you is that if you know what Z is, it tells you the probability that goes with it. That's what the Z table does. So that's what I'm going to write down here on my piece of paper. Stop sharing that. Nope, not that one. That one. So the table says that you know Z, and it tells you the probability that goes with it. That's how the Z table works. So you look up Z inside the term on the edges of the table. You look that up in the margin of the table, and it tells the probability in the body of the table. That's how the Z table works. So if you know a value of Z and you're looking for a probability, then that's what you need to do. And that will happen when you're trying to do probability problems with normal distributions where you're asked to get an answer that's a probability, or when you're finding a p-value, you're trying to get a probability as your answer. That's one of the things that we are looking up. And I will just do some examples later and we'll see how they all work. But if you know the other way around and you know a probability and you want to find the Z that goes with it, that's a little harder because you're trying to use the table backwards. You need to find the probability you're looking in the middle and then look at the edges to see what Z goes with that. Right. So before I do the examples, I do want to just do this. Now I will do an example. For example, scores on psych questionnaire. Are normally distributed with a mean of 25 and a standard deviation of 3. What what percentage of people will get a score of 27 and above? That's my question. So I've been given a situation that's about normal distributions and it's about probabilities. And so I'm pretty sure I'm going to have to use that table. And so my only way to get there is to turn my probabilities that I've got, my distribution I've got, into a Z. But I'm just going to start with this. Let S be the score. And then this is what the distribution of S looks like. It's got a 25 in the middle, and then it kind of goes up in 3s and down in 3s. That's kind of what I'm thinking about there. And then you get to almost all of it once you've gone 31, 30. Once you get to 34, you've covered pretty much everybody. Okay. So what they've asked me about is the number 27, which is here. And they say they want the people who are 27 and above. So that's these people. That's 27 and above there. So 27 and above is that way. And I want to know what percentage of people get that score. The areas is what represents my probabilities and therefore my percentages. And so this is a drawing of the story here. If I was in Excel, I could do this now. I could tell it norm dist and tell it what the mean and standard deviation is. But if I have to use the table, I'm going to have to convert to Z. And to convert to Z, you have to take off the mean and divide by the standard deviation. That's how to do it. Because what Z is counting how far away from the mean you are in terms of how many standard deviations that's worth. That's what the Z is for. And so I need to know how far from the mean. And then when I divide by 3, that's how many standard deviations is that? And so when I do that, this is S back here, the Z will have a mean of 0 and a 1 and a 2 and so on. So that 25, it'll become 0. And that 28, it'll become 1. And that 31, it'll become 2. Because that's what we're doing. I was counting in standard deviations before, and they were 3s. But now I'm counting in standard deviations, and I'm literally saying how many standard deviations have I gone past. And so the probability is the same, like it looks the same. Technically, my drawing has to get higher or lower, but I've just remarked the axis in a different thing. And I need to figure out what that 27 becomes. So this number here is 27 minus 25 divided by 3, which is 2/3, which is 0.66, something like that. So now, what I wanted to know was the probability that the S is at least 27, which means I need to know the probability that Z is at least 0.6667, because that 27 became a 0.6667. And unfortunately, my Z table doesn't tell me the right-hand side, it only tells me the left-hand side. So I have two choices. I can either look up the left-hand side and then figure out what's left when I take that from 100%, or I can know that the normal distribution is perfectly symmetrical and look up the left-hand side of minus 0.6667. Either one of them works, but the one that makes most sense to most people is to now do this. That's 1 minus the probability that Z is less than 0.6667. Like that. So the picture in my head is that we're actually going to do, we're going to ask the table for what this bit is, because the table's only capable of doing left-hand sides. And then this bit must be what's left. All right, I'm going to have to skip over to the table. 0.6 and then 7, I guess. That's the nearest one, yeah. 0.67, that's the nearest number. So this is 0.6, and then the next decimal place is 7. So I had 667, so that rounds off to 0.67. So just a second, just for my own purposes, I'm just going to go back to my drawing and say, all right, I'm going to round it up to 2 decimal places because my table's only got 2 decimal places. I really should have paid attention to that. I put 4 in, but it's the probabilities that have 4 decimal places, and it's the, okay, 0.67. So I'll have to go do that. So 0.6 and then 0.67 is here. Have I got that right? Go up 0.767. And so I'm going to write that down. The probability that Z is less than 0.67 is 0.74857. Okay, that's what the table says. And so therefore the probability that Z is more than 0.67 is 1 minus that answer, which is what calculators are for. 0.3, no, 0.262 probably. Really going to do a calculator. I have everything off by 1. There you go. So 25.1% of people have scores 27 and above. Okay. Yay. That's how these things work. I just want to show you the bit up here. If I turn my graph backwards, you can just see underneath there, the one going the opposite way. If I flip my graph over and look at the probability below the negative version of my number, so negative 0.67, I think that was here. Yep, 25143, number I got before. So you can also, because you know that it's symmetrical on either side, you can do the probability above a positive number is the same as the probability below a negative number. So that's a fun game. But even if I was in the exam, I would probably not think of that either. You have to be thinking very clearly and be not stressed to do that sort of thing. Yeah. So that is using the Z table to figure out a probability. But if the problem had said which score has 30% 30% of people scoring below it, but which score has 30% of people scoring below it in that same story? That's giving you a probability to begin with and asking you the Z, the X that goes with it, or whatever it is, S that I called it. And so we're using the table backwards now. Now we know that the probability of Z being less than some unknown number that we don't know what it is has to be 30%. And so we're using the table backwards now. We have to look up the 0.3 and find the right number that goes in this spot. I should probably give this a name. I don't want to use a small z because I won't be able to tell it from my big Z. How about we call it C for cutoff? That sounds good. And so in my diagram, there's C there, and there's 30% there. And I have to go and look up in my table to get my probability of 30%. So let's see, where's my table? 0.3 I'm looking for. Well, there's 0.29, 0.298, 0.301. So it's one of those two. It's somewhere between there and there. That's when it switches over to exactly 0.3, somewhere between here and here. 298 would be 002. Oh, look, I'll just go halfway. That'll work. So the table, whoa. The table has, so in the table, for minus 0.50123, probability that Z is less than that is 0.30, just a second, 0.12, it's 0.299806, and the probability that Z is less than minus 0.52 is 0.30153. Damn it, I've gonna go. No, did I just share the same thing again? So this is what I'm copying from the table. I was at minus 0.53 and it gave me this, and minus 0.52 and it gave me this. And so that's this picture here. Minus 0.53 and minus 0.52. And somewhere in between them is when it's 0.3 exactly. That's what we're imagining. So most people will go halfway between. And so we're going to say that C is going to be minus 0.525, which is halfway between these two numbers. Because 521 would be a little bit further this way, 522 is a little bit further this way, and 525 is pretty good. That doesn't actually answer the question. This is telling me the Z score that goes with this. And so this is how many standard deviations below the mean we are. So this is number of standard deviations below the mean. So the actual distance is going to be that many times 3 because the standard deviation was 3. Distance below mean is minus 0.525 times 3, which is whatever it is. And you don't have to actually calculate this, but I'm still going to do it. 0.525 times 3. And therefore the actual value is the mean, which was 25, wasn't it? Yes. Minus that number. $23.425. There you go. That is the number that has 30% below it. Cool. So everything's backwards, right? The other one before I took off the mean and divided by the standard deviation, and this time I times the standard deviation and added the mean. So they're complete opposite directions. How are we feeling about that? Okay, so that's using the Z table, but it also comes up when you do hypothesis tests if you want to find a p-value. So I'm just going to do that now because even though it's it's like 7 weeks apart in the course, it's the same skill. So I'm going to do one more example with a p-value. So here's my example. Do I want to do this? We surveyed like 200 families. And asked if children. Oh, I have a question. Do you do p-values when you do think with proportions or just with means? Did you do like a z-test for like, is the proportion actually 0.8? That sort of question? Does that sound familiar? No? All right, then I won't do that. I've changed this course in the last couple of years and I don't always know what's in it. So I will not do this. I will not ask this yes/no question of the children. We surveyed 200 families of teenagers and asked how much their bag weighs, their school bag weighs. And the sample mean was 3.2 kilograms with a standard deviation of 0.6 kilograms. That's what I'm going to say. Am I going to say that? Sure, I'm making up numbers. I know my daughter's school bag certainly feels heavy. Anyway, let's run with that. Want to know if the mean weight is above 4 kilograms. And we'll do a test to answer that question. Okay, so this is a classic hypothesis testing situation because the implied question here is a yes or no question. Is the mean weight above 4 kilograms? Yes or no? That's yes or no question, and that's exactly what hypothesis tests are designed to answer. They're designed to answer yes or no questions. And it's a yes or no question concerning the value of a mean, which is this here. Cursors. Wait, I need one extra piece of information here to be able to use a Z. So people were wondering how to decide whether it's a Z or a T. In this context, the most important thing is that we have to know what the real population standard deviation is. And so we're just going to say last time the standard deviation was 0.55 and assume this is the population standard deviation. Okay, that's my extra bit of information. We're going to assume that the population standard deviation is 0.55, like it happened last time. So even though in my sample I got 0.6, I shall ignore that because I'm going to assume that it is the population standard deviation. We'll come back to that. So this piece of information here is what tells me that it's a Z. If I didn't know that and I had to use the sample standard deviation, then I would be doing a T. But since I've been told the population standard deviation, then I can use a Z. That's the difference. Sometimes I wish we lived in the land before T, when they used Z for everything and they didn't know that they should use a T. But thank you, Gossett, who discovered the T distribution. I mean, the world is, our calculations are more accurate than they used to be. But I still wonder whether we really need to be that accurate, honestly. But here we are. Nothing like, I mean, it's classic fodder for any university course to have lots of different situations that you have to respond differently in. Happens in law courses too. Yeah. Happens in physics courses as well. That's just the way life is. Sorry, everybody. That's university. University, yeah. If we didn't ask you to do anything, you wouldn't have anything to do. They've given us this information, and so I'm going to write it down in symbols. And so my symbols are that my X bar, it's traditional to call them sample mean X bar, is that right? Yep. My X bar came out to 3.2, I think it was. Yep. And my population standard deviation, which is represented by the Greek letter sigma, lowercase sigma, is 0.55. They have told us the information that the sample standard deviation is 0.6. But since we have been told what this one is, we're going to use that one. But this is the information they've told us. And we are wondering if the mean is really 4. So the question we're asking, that's the question. Is the real mean, mu, is it equal to 4? So this is the information we've been given. And if I was doing a null hypothesis test, I would say the null hypothesis is that the mean really is 4. Is that how they write it, with an H0? And they probably do an alternative hypothesis as well. Do they use a capital A here? Yeah, okay, cool. And that would be that the mean is something other than 4. I'm just checking, in this course, do they do two one-sided ones with a greater than and a less than? Or do they just only do not equals? Okay, so they have all 3 of those options. Cool. All right. They want to know if the mean is above 4 kilos. They've been very clear about the aboveness of it. So I reckon we want that it's... What the hell? Just a second. Obviously, haven't been here for a long time. So they're really interested in knowing if the mean is above 4. I'm going to write the greater than sign. Doing okay? So if they had just not had that word above, and it had just said, where is it? And it had just said, pardon me, they want to know if the mean weight is 4 kilos, then I would have put a not equal to sign here. But they've, yeah. So as I just want to point out, one word can make the difference. So read carefully. And a useful thing to ask yourself is, if one of the words here had been removed, would I have made a different decision? And the answer is yes. If it hadn't mentioned above, I would have said not equal. And so that must be an important word that they've told me. Yeah. Okay. And so that means that I have to calculate a statistic. And traditionally, if I'm going to use my sigma, and I'm not going to use that because they've told me what sigma is, then I calculate a Z statistic. If I was using the S, I would calculate a T statistic. So we know sigma, so we'll use Z. That's what we're thinking. So Z is the sample mean minus the mean we're comparing it to, which is 4, divided by the population standard deviation on root of the sample size. Oh, they told me you did that too, didn't they? They said 200, didn't they? I'm talking about it as if it wasn't me. I'm saying they. Made it up. 200. So just the formula normally looks like this. Like that. They might not put a 0 there, but some lecturers do put a little 0 there to remind you that it's the mean that belongs to the null hypothesis. And that will come out to an answer, and I really am going to use a calculator for that because nobody wants to do a square root in their head, or indeed can. I'm sure there are some people who learn how to do that. Wow. Cool. Minus 20.57. I'm very sorry, people. I'm just going to change my question. Now, just at the moment, the reason I said that is, you know how I said that almost all the probability is covered when you go past 3? And we're at minus 20. We already got to nearly all of it at 3. This is really, really low. So I would reject my null hypothesis no matter what, right? That's a really small number. So I'm just going to change the sample size to something. Oh, wow. Cool. Bear with me. I'm just going to change the question so that we get something that's look-upable. All right, changing the question. Sorry about that. Question is changed to 20 families and 3.8 kilos. Okay. And this answer has become, this answer is now minus 1.626. Okay. All right. So I'm just going to draw a picture of my situation. Here's minus 1.626. And here is the probability of the Z being more than that. And the reason I've done the more than is because this was a more than. So my p-value is all of this. Which is like, more than a half, right? That's half there, so the probability is more than half. Usually the cutoff for a p-value being low is 0.05, and we've got something that's more than 0.5. So, but just going to actually look it up in the table though. Still, 1.626. So 1.63 if I want my table to be able to do it. So, oh crap, that's the right-hand side. My table only gives me the left-hand side. Okay, so that's 1 minus probability that Z is less than minus 1.63. Okay. So I'm going to actually ask the table, this is the bit I want, and this is the bit that's actually in the table. Okay. Minus 1.630123. 0515. Okay. Wow. Wow. So 0.9 something then. Whoa. 0.94845. That's my p-value, which is, huge. Because the usual place to cut off a p-value where you decide to reject is at 0.05. This is a long, long way from 0.05. And so I'm not. Does your lecturer say retain a null hypothesis? Do they say do not reject the null hypothesis? Do not reject? Okay. So I do not reject the null hypothesis and conclude that the mean is not more than 4. Yeah, like it could be 4 as a possibility, but it's just not this one. So no, mean is not more than 4. Okay, cool. That was unsatisfying. It's always nice to reject it. But that is one of the ways to deal. We did the same move that we did before. As soon as we turned it into a question about a Z, we could go look it up in the Z table. And that's how to get p-values from the Z table. Okay? Right. It is very uncommon for a p-value to be, 95%. Okay. I mean, it's hardly surprising. 3.8 is like less than a whole standard deviation away from 4. It's not enough for me to decide that the mean's not 4. So, well, unless you had 200 of samples, because the more samples you get, the bigger the size of Z becomes, because the biggest, more the denominator is, and yeah, so the answer is bigger. Okay. So I have officially 2 minutes left, but I am just going to, I really want to talk about the t-table so that it's done. So if you have to go, I will not feel offended. So with t-tables, oh, bear with me, just thinking. Okay. I have missed something with the confidence intervals, but I just want to make sure I talk about this. So the t-table is based on the t distribution. And I'm pretty sure they gave the letter t because it was the next available letter that hadn't been used for anything yet. So we'd already used z for the normal distribution. We've already used x and y for x and y on a graph. U had already been used for integration. So t was like the next thing that was available, so they just called it t. And the t distribution, to the naked eye, looks like a normal distribution. But it's not. In fact, I reckon I can just a second. It looks like a normal distribution. That's what the t distribution looks like. But each t distribution has a different number that can go to tell you which t distribution you've got. And that's called the degrees of freedom. I think it's a bad name for what that is. For me, it's the DF stands for distribution finder. So just like with a normal distribution, like not the standard normal, the Z's always the same, but a tradition, like any random normal distribution can have a different mean and a different standard deviation. The T distributions have different standard deviations depending on what the degrees of freedom are, just slightly. And I'm just going to put in as well the normal distribution. So the blue one there, the one that just turned on, that's the normal distribution. And this red one is the T distribution with different degrees of freedom. And so if I've got 6 degrees of freedom, then it's just a little bit below the normal distribution in the middle and just a bit above the normal distribution on the ends. And that will always be true of a T distribution. If I go down to 1 degree of freedom, it's really extremely below the normal distribution. And the higher that degrees of freedom gets, the higher the graph gets. And the closer and closer and closer it gets to being a normal distribution. Twelve, 13, 14. Once we get to about 15, we're nearly at the exact, it's pretty close. I mean, it's not exactly, if we zoom in on this spot here, it's not quite there. If I put like 100, still not quite. But if I zoom out here, like, you won't be able to tell from this distance. But it's never quite equal to the normal distribution. It just gets closer and closer and closer. And that is what Gossett, I've forgotten his given name, but I know his family name is Gossett. That is what Gossett discovered in about 1910-ish. I can't remember the exact date. Most of this statistics was invented between like 1890 and 1930. So, yeah. And so the problem with it is that there's only one Z distribution. Like you can convert any normal distribution to a Z distribution, and that's fine. But there's a different T distribution for every degrees of freedom. And so you have to know which one you've got to be able to calculate your probabilities. And we can't have that giant table that we had for Z for every different degrees of freedom, or we'd have to have like 100 tables. Now, Desmos has the T distribution programmed into it. You can just ask it for probabilities. And so does Excel, and so does lots of different calculators. And so these days, most people just use a computer to tell them the probabilities that go with the T distribution. But what you have is a table. And it looks like this. And so see here, there's a column here that says DF. That's the degrees of freedom. And so that is the thing number that I was changing that made my distribution get closer and closer to being normal. And if you scroll all the way down to the bottom, see how it has a Z at the bottom? That's what it's trying to get at, to say that the higher and higher this degrees of freedom gets, the closer and closer to being a Z you are. And so Z is like the infinitieth T distribution. It's the last one. I was very pleased that in the Lego movie, Lord Business lives on the infinitieth floor of his building, because that's what Z does. Z lives on the infinitieth floor of the T building. And that appeals to my brain. So this table is not at all obvious what the hell it's trying to say if you're used to the Z distribution. This is the reverse of the Z table. The stuff in the body here, they are the values of the statistic. Back with the Z table, the things in the table were probabilities, in the body were probabilities, and the things in the margins were values of Z. Well, the T table's backwards. The things in the body are values of T, and the thing in the margin up here, they're probabilities. That's the difference. It's the reverse. And so when I have the, degrees of freedom, 10 degrees of freedom here on the last blue row, last of the first blue block there. And so this is saying that, see that T50? That's saying that if to get past 50% coming in from the left, then 0 is the spot. And of course they're all 0 because the T distribution is symmetrical. Halfway is 0. If I want to go past 75% of them, then in the 10 degrees of freedom, I need to be at 0.7. If I want to go past 80% of them, then I need to be at 0.879. All the way, if I want to be past 99.95% of the values of T, I need to be at 4.587. So what this is trying to do, I'll just zoom out a bit again. And I'll go back to 10 degrees of freedom. I'll turn off my normal distribution. If I'm at 0.5, if I'm at 0, there's exactly half the probability to the left of that. If I'm at, what did my table say? If I am at 0.7, there's 0.75 as my probability to the left of that. I'm 3/4 of the way in terms of probability. And if I'm at, let's just see if we can make, I want to get it to 80%. What's my table say? So if I want to get to 80% on the left, I'm going to need that 0.88. That gets me to 80%. And so what that top row of the T table is doing is it's telling you where you are in terms of probability. And I don't know why it's given it this way. That's the way it is. What the next row here is telling you is the probability on the top end. So this bottom bit is telling you the left-hand probability. The next row is telling you the right-hand probability. Look at this. See, 0.8 here, and that's 0.20 there, 0.75 there, and 0.25 there. They add up to 100%. I don't know why my highlighting's done that. And what this one is doing is telling you twice the one above it. So if I go back to my paper, what the T table is telling you, the top row is telling you the area so far. The second row is telling you the area above. And the third row is telling you the area on the outside if I copied it on both sides. And you're based on the value of T in this spot here. So this is in the margin. The top margin is all of this stuff in the T table. And then the body is values of T for each degrees of freedom. So the thing about the T table is it can only tell you probabilities that are in that top row. So the Z table could tell you any probability you wanted for any value of Z, but the T table can only tell you the probabilities that are for numbers that are in that top row. Like sorry, it can only give you answers for probabilities that are in that top row. And so when you calculate a p-value using a t-distribution, you can't ever know, using the table, you can't know exactly what the p-value is. You can just know, well, it's between this number and this number. So if I did, as an example, collect bag weight data again. Don't want to assume a population standard deviation. And this time, the sample mean is 4.3 kilograms, and the sample standard deviation is 0.2 kilograms. Oops. Going to still have 20 people. We want to know if the true mean more than 4 kilograms again. So similar situation, I've changed the numbers. So I've got my N is 20, there's still 20 people. The sample mean is 4.3. The population standard deviation we don't know, but the sample standard deviation is 4.3. Sorry, no, 0.2. Just know that if they don't tell you anything about the population standard deviation, you just assume that you don't know it. And then the question is the mean equal to 4? That's the question. And so my null hypothesis is no. In fact, the question is it more than 4, right? That's the question they're trying to answer. So my null hypothesis is that it's equal to 4 because you have to pick a number for it to be equal to in order to do the calculation. And the alternative is that it's more than 4. And this time I will do a t statistic, but it will be done exactly the same way. X bar minus the mean from the null hypothesis over the sample standard deviation on root n. So 4.3 minus 4 over 0.2 on root 20. Four point three minus 4 divided by 0.2 divided by 6.71. So I can't know the exact p-value of this, but I can go and look it up. And so I need to look up. Now, just a second, I need to look up in the correct degrees of freedom. When you're doing a single sample like this, the degrees of freedom is n minus 1. Look up degrees of freedom 19. And I'm going to need to look up that 6.71. And actually, just to be clear, I need to know exactly whether I want to know both sides or one side. And they said a greater than, so I just want one side. If it was a not equal to, I would have done both sides. So let me go look up 6.71 in the table. There's 19. 6.71, okay, 0.6, 0.8, 1, 1, 1, 2. Okay, it's off the end of the chart. 6.71 will be over here after the 3.833. Okay. 3.833. And that 3.833 goes with a 0.9995. Okay, so we know that the probability that t is more than 3.833 is 0.9995. No, it's not. That's I did it to myself. The top row is the left-hand side. I want the second row because that's the right-hand side. I said that, and then I didn't do it. Sorry about that. And my number is further out than that one. And so therefore the p-value, whatever it is less than 0.0005, because we're saying that if it was 3.6.7, if it was 3.833, then that bit over there would have been 0.0005, all of this. And so the actual p-value has got to be less than that. I'm just going to do a what if. What if the t had been like 1.4? Then I would have gone and looked up in my row 19. No, from 1.06, 1.3, 1.4 is between here and here. I'm just going to write those numbers down. So the probability of t being more than 1.328 was 0.2, and the probability of t being more than 1.729 was 0.10. That's what the table says. So just drawing a picture of that. There's 1.3, and there's 1.7-ish. And this bit here is 0.2, and this bit here is 0.1, which means my number, which was 1.4, must be somewhere in between. And so the p-value is between 0.10 and 0.20. And if your cutoff is 0.05, which is what it usually is, then you would not reject the null hypothesis. Whereas back here in this one, this p-value is shockingly small. And so I would reject here because that number is really small. Whereas in this one, I would not reject because that number is not small. Usually the cutoff is 0.05. So not reject. At the 5% level, for example. You have to read your exam question to know what percentage level it is. Because at the 10% level, I will still not reject it because it's more than 10% as well. So, yay, okay. At the 20% level, I will reject because it's definitely less than 20%. But it's the 5% level is the most common one. And if they don't tell you a percentage level, you'll just say, we'll use the 5% level. Because that's the most common one. Because that's the one that Fisher used when he invented hypothesis testing in 1925. And no one has thought to choose something better since then. Because 5%, people understand what 5% means and believe it. Yeah. So that's why the t is different, because it only can tell you the p-value for some numbers, and so you're just going to have to say yours is between these numbers. But the other option is to choose a rejection region. So you could have done or at the 5% level, the t statistic that goes with that goes with exactly 5% on this side, would have been, where's our 5%? That one there. Oh, damn it. I did the two-sided one before. Then moment. Just going to have to go fix my other one. I did the two-sided one. I read the wrong row of the table. Because I went up to the first row of the thing at the top. Let me go back and fix that. I'm just going to write this down, 1.729. Sorry about that. Let me just go back and fix what I did. This was 10, and this was 05. I still reject at the 5% level because it's definitely more than 5%, because it's between 0.05 and 0.10. That's okay. So at the 5% level, the t-statistic that goes with the p-value of 0.05 is 1.729. And so this is the critical t-statistic. I don't know if you've heard that word. Yep. So my t-statistic is 1.4, which is not further out, and so therefore we do not reject. It's the same idea. Like you're literally just drawing the exact same picture as this, but you're only drawing one of them. You just want to know which side of this your number's on. And if you're further out, then you reject, and if you're further in, then you do not reject. So the nice thing about using a rejection region is you only have to look up one of them in the table. You don't have to look up more than one. Whereas if you want to get a probability estimate, then you need to look up the ones on either side. You need to look up two of them. So that's the way it is. It really is time to stop because I have another seminar starting in 10 minutes. Please, if you want to talk about any of these things, come to the Maths Learning Centre and we can chat about it. And I wish you calm nerves and clear thinking and, well, safe travels to your exam.